complex adaptive systems. However, we can make probabilistic prediction. So we can say that we have a higher likelihood that this might happen if we act this way, but we can't be certain. We have to deal with uncertainty. And the presence of feedbacks, they can be positive or negative. Negative feedbacks normally stabilize the system, as in the Gaia theory, and positive feedbacks might destabilize the systems. And then it's distributed in nature, so it becomes very difficult to locate functions and processes and properties of these systems. There is a huge qualitative difference between larger and slower functions and smaller and faster ones. And there is, as I said before, limited decomposability. So, as the structure of this system is very important, if we look at only individual parts, we will not be able to understand the behavior of the overall system. So the scale is very important, depending on what we want to analyze and how we want to analyze. It's fundamental to get the scale right. And is this like, for example, this is a scale example. What do you see? Imagine you're analyzing a system and you see this. How would you describe this image? Yeah, but actually it's wrong because it's a math. So depending on the scale you're in, and if you scale out, you find the tavern and then a painting. However, if you get the scale wrong and you zoom out too much, you might not be able to understand anything anymore. See the painting is over there, and you can't really see any details. So it's very important to understand, especially when we couple human and ecological systems, and we want to get the management right, is the scale is fundamental. So scale mismatches can lead to really bad outcomes. Okay? And this is more and more important, especially now that we start to understand that a lot of systems with the towers separate are actually interconnected. And the problem is that at the management level and the social level, we are not that interconnected. Okay? So we might be interconnected in a small world sense. So I know somebody that knows somebody, but we don't talk to each other. We don't manage at the right scale. And that might be a huge problem in the future. Actually, it is now. And it might become harder and harder to solve in the future. And actually, I'm not sure if this works. This is a video. It's Eric Berlo that talks about scale. It's a 3-minute video, but I'm not sure my audio is good enough. Shall we try it?
Yeah, that's fine.
With your mic.
Put your mic on.
plot the
into this. So let's do it. So here you go, for the first time ever, a world premiere view of this spaghetti diagram as an ordered network. The circle node is one we're trying to influence popular support for the government. And so now we can look 1 degree, 2 degrees, 3 degrees away from that node and eliminate like 3/4 of the diagram outside that sphere of influence. Within that sphere, most of those nodes are not actionable, like the harshness of the terrain, and a very small minority are actual military actions. Most are nonviolent, and they fall into 2 broad categories: active engagement with ethnic rivalries and religious beliefs, and fair, transparent economic development and provisioning of services. I don't know about this, but this is what I can decipher from this diagram in 24 seconds. When you see a diagram like this, I don't want you to be afraid, I want you to be excited, I want you to be relieved, because simple answers may emerge. We're discovering a nature that simplicity often lies on the other side of complexity. So for any problem, the more you can zoom out and embrace complexity, the better chance you have of zooming in on the simple details of the diagrams. Thank you.
Questions? So the importance of scale. And the second thing is that complex systems are characterized by self-similarity. So this is a fractal. Are you familiar with fractals here? Basically, is Mandelbrot was the first one to discover this, thanks to the IBM laboratories. It was hard to access that kind of power at that time. And he basically found out that there are structures that repeat themselves over and over again. It was a way to calculate the coastline of Great Britain. And that's how they did it. And some complex systems display this type of pattern. And obviously what is very interesting for us is the emergent properties of the complex adaptive systems. Like, we can't really predict what is going to happen by looking at individuals. And this is key. For example, if we give individual rules to these people, we will never predict that no accidents happens. It's very unlikely, but this is actually happening. This is just human behavior. And it's very difficult to model. It's actually very challenging. But that's what makes it fun, I think. You know? People actually think sometimes. And they self-reflect, and we have different types of learning, different types of applications. Okay? Kind of similar to as well where I'm from. And this is an example of a complex adaptive system. So it involves many components, dynamically interacting, a number of levels of scale, they have common behavior. And we can go from composites, so we have simple systems, but then as we scale out of it, we start having self-organization, and then we get emergent behavior, and we get complex systems. Even though these scales seem big, actually those can be a size or maybe very complex. Human beings, human bodies are really complex. And actually the example of the temperature is a great example for resiliency. Because human body is very resilient. We stay at that temperature under a huge variety of conditions. Though when we tip, then it's when we have problems. Or and if we tip too much, we're not coming back. So, and that is a problem with when we deal with natural resources. We might not get into these feedbacks, we might not take into account human components. We decide we have a great policy in place, but then people behave in a completely unpredictable way. So sometimes and there are examples by a paper by Liu in Science in 2009, was showing how in establishing a protected area without the support of the people, it might actually have very detrimental effects. Because people start logging or start going into the forest, no one is controlling because that is also a problem. And people just change their behavior just to go against a decision that they don't feel it's legitimate. They don't feel they have been involved in. So these top-down approaches might create a lot of problems, though we sometimes need them. We need to combine them with some other approaches like community-based. And for doing that, we need to combine your knowledge as natural resource science with knowledge of people in the field that work with communities, and also try to participate, to make these people participate in the formation of models and in the formation, and try to integrate their feedback, their behavior into what we're trying to do. And there are different ways to analyze the complex adaptive systems. Now, nonlinear dynamics, I guess you're all familiar with it. Statistical mechanics like phase transition and critical phenomena. Some network theory. that we'll talk about, I think, Thursday, right? Yeah, perfect. So one way to analyze complex relative system is to look at critical values, and they look at, and so looking at boundaries between different regions, so a stable region, and then something happens and the system completely shifts. It either shifts baseline, or it becomes unpredictable, or it starts cycling, and then it starts becoming unpredictable, right? And then, you know what percolation? They're often characterized by percolation or by thresholds. So up to a certain point, everything is fine, and then you change just a bit, and the system shoots up. I'll show you an example in a second. So this is done in that level, and this is basically this is a density and a percolation threshold. So if we go, we can see here we have a transition. This is a phase transition. The system is fairly stable. It's okay. And then suddenly the giant component, like all the red bits, even when the density is more or less half, it starts growing a lot. Okay? Is that clear? Yeah? No, so we actually need models. Now I have problems here, I don't, but a lot of times I had problems in why you don't take this into account in the model, why you don't do that into the model, why you don't take this behavior into account. Now obviously that's not a pipe, and that's not a solar system. And this is obviously not a library. But it's just a useful way to represent it. So what we need to do is to find the fundamental variables, the fundamental processes and controls of a system, and portray those. We don't need to overcomplicate the model. We need to keep it simple. If not, we don't understand what's going on anymore. Or we spend like years to understand just the model and not the reality that it wants to represent. And there are different ways to model systems. Statistical modeling is very used, especially in economics. But it might have some problems. It's often assumed homogeneity. It often assumes an average behavior or average people. But as you can see, if it's the average depth is 3 feet, it doesn't mean that it's 3 feet everywhere. It's the same thing with income, for example, generation. Or the average income of a country doesn't mean much. It's distribution that is much more important. Because if 2 people have a lot and a lot of people have nothing, they might have the same mean as everybody's equal. So, and those are actually what might make it different, especially in a human system. We can model systems with differential equations or partial differential equations. We can even numerically simulate them. Actually, I don't think that the models you showed, they have closed form solutions, or do they? Or they are only numerically simulated. The model you showed before.
What do you mean by closed form?
Like, can you find a perfect solution? Like, if you have the parameter in a certain way, you have one solution, and it's deterministic every time you have that, you will have that solution. Or you can only numerically simulate.
That's one of our tests.
Converge.
Yeah. Does it converge?
We can always reproduce our results. We cannot do this anymore with the computing. But we do make, no, I mean, that's not trivial exercise, which we can reproduce our results.
Oh, yeah, it's the same problem for us.
They don't always have unique solutions. You can have started with the computer. With the same initial conditions, always get the same.
Sorry.
With the same initial conditions, you always get the same.
Oh, you always get the same results.
Yeah.
Like,
This requires a lot of testing to make sure that nothing goes horrible, even marking the limitations. And not every one is about that.
You can also add humans and make emergent solutions instead of just converging.
And then there's another way to model these systems, and here's the way I normally use. It's called agent-based models, or individual models in ecology. And there are simulations of the system from the bottom up. So what you actually do is to make here individual entities behave according to certain rules, and you try to model their interaction, and then you let the model run and see what emerges. Okay? So you can have actually agents that adapt their behavior, they learn. We'll see different ways of learning. They can learn by in a genetic algorithm, so in the evolutionary sense, or they can learn because because they've done certain things in the past and they work good.